Hi everybody. In this video, we're going to talk about dilations. So dilations are a type of transformation that make things bigger or smaller depending on the scale factor. A dilation changes the size and possibly the position of the figure, but it does not change the shape. So as you can see here, if the scale factor is greater than 1, like 2, it will make the image bigger. So notice how the pre-image is triangle ABC, and the image is double the size of the original because the scale factor was 2. Notice how here, when we have a scale factor that is in between 0 and 1, like 1/2, zero point 0.5, it makes the image smaller. So the triangle got half the size of the original. Here we have a scale factor of negative 1.5. That's greater than 1. So it is going to make it bigger. But what it does, notice how in the positive examples, like the positive scale factor of 2 here, the distance of the triangle from the center of dilation is increasing. It's doubling the distance from the center of dilation. But notice here, the image is going to the other side of the center of dilation. So it's not going further away from it, it's going to the other side of it. Same thing here, it's making it half the size, but in the other direction because the scale factor is negative. So a couple of things about dilations. Dilations preserve angle measurement. So since dilations change the size of a shape, they don't make congruent figures. What they make are similar figures because they make figures that have proportional sides by a certain scale factor. So dilations do not preserve side lengths. The sides change, they get either bigger or smaller. But since the triangles are similar, since their corresponding sides are proportional, the angles stay the same. Remember, similar triangles are proportional sides and congruent angles. So under a dilation, sides change, but they are proportional. Angle measurements stay the same. Dilations preserve parallelism. That's an important one. What that means is that the pre-image and the image after a dilation will be parallel to each other. And that's going to be important when we take a look at line dilations, which is coming up in a little bit. And orientation, for the most part, dilations do preserve orientation. They might change position a little bit, but overall, for the most part, they just get bigger or smaller. The orientation generally stays the same. In this first example over here, we have the line 2y equals x plus 8, and it's being dilated by a certain scale factor centered at the origin. And the image of the line has this equation over here. We need to find what the scale factor was. First, I'm going to take the original line and I'm just going to rewrite it so that it is in y equals mx plus b form. So I'm just going to divide everything by 2. And remember, there's an invisible 1 in front of the x when you don't see a coefficient. So what we have is y is equal to 1/2 x plus 4. I'm going to do the, oh, that looks like a 9. Let me change that. It's plus 4. I'm going to do the same thing for the image line. I'm going to get y by itself by adding 1/2 x to both sides. And that would be y is equal to 1/2 x plus 2. So let's see how it changed from the original to the dilated line. Notice how the slope stayed the same. And that makes sense because dilations preserve parallelism. So the pre-image and the image should be parallel to each other. And parallel lines have the same slope. So anytime you dilate a line, the slopes will remain the same because the lines will be parallel. Let's see what happened from the y-intercept of the pre-image to the y-intercept of the image. Notice how it got half. It went from 4 to 2. So that tells us that the scale factor here is 1/2. And that works anytime you have a dilation centered at the origin. The slopes will stay the same, but the y-intercept will change by what the scale factor is. So from this to this, it's multiplying by the scale factor of 1/2. We can check out this next one, and they give us the equation of a line again, and this time they give us the scale factor, and we need to find the equation of the image. Well, we know that the slope needs to be the same as the original because the pre-image and the image after a dilation will be parallel. They'll have the same slopes. So I'm going to rule out 1 and 2 because those don't have the same slope as this one here. So I'm between 3 or 4. So I'm going to take the y-intercept and I'm going to multiply it by the scale factor. And on my calculator, if I do -4 times 3 over 4, that gives me -3. So that gives me answer choice number 4. Moving on, we have some more examples. We have a dilation centered at the origin, and if the question doesn't specify, we assume it's centered at the origin, with a scale factor of -2. When we have a point that's centered at the origin, the way that you could easily dilate it is you could just multiply the x and the y coordinate by the scale factor. So 8 prime would be 1 times -2, which is -2, 5 times -2, which is -10. And the question's asking what quadrant this would be in. So -2, -10 would be somewhere over here. This is the first quadrant, second quadrant, third quadrant, and fourth quadrant. So it would be located in quadrant number 3. Okay, here we have the equation of a line, and there's an invisible 1 when you don't see a coefficient on the x, so the slope here is 1, and we're dilating this by a scale factor of 1/2. Now, if it doesn't tell you it's centered at the origin, we assume that when it doesn't specify. So we know that the pre-image and the image will be parallel to each other. So it does have to have the same slope as the original. So it's going to have a slope of 1. And we know that we can use our rule, multiply the scale factor by our y-intercept. -4 times 1/2 is going to be -2. So we have the equation of our line is y equals x minus 2. Let's take a look at some practice questions. You might want to pause the video and take a look and try to answer the questions on your own first. If triangle ABC is dilated by a scale factor of 3, which statement is true of the image A prime, B prime, C prime? Answer choices 3 and 4 are talking about the angle measurements changing, multiplying one of the angles by something to get the other angle measurement. But we know that when we dilate a figure, the angle measurements don't change. It makes similar figures, but similar figures have congruent corresponding angles. The side lengths are the only thing that's changing. I'm going to rule out 3 and 4 automatically without even looking too much into them because nothing about the angle measurements is going to change when you're doing a dilation. Okay, now let's look at the difference between 1 and 2. 1 is saying that if I take the image and I multiply it by 3, then I get the starting line segment. That's not what happens in the dilation. In the dilation, you take the pre-image, the starting line segment, you multiply that by the scale factor, and that gives you the image. That's what answer choice 2 says. Take the original line segment, multiply it by your scale factor, and then you get the image, B prime, C prime. So 2 is our correct answer choice. If you take a look at number 2, it's not going to be as easy as the other examples because the dilation is not centered at the origin. It's centered at point A. And point A does not have the coordinates 0, 0. It is not at the origin. And we need to dilate this by a scale factor of 2 centered at point A. Let me make this a little bit bigger so you can see what I'm doing. And so also it'll be easier for me to see what I'm doing. There we go. Let me move over here. So I'm going to do this using slopes. I'm going to do this visually. So remember at the beginning, we talked about how a dilation is not only making it bigger or smaller, but the way that it does that is by changing the distance that each of the points is from the center of dilation. So a scale factor of 2 basically means that we're doubling the distance that each of these points is from the center of dilation. So right now, from the center of dilation, point B is 1 space over and 1 space down. So if I want to double that distance, I'm going to repeat that movement. I'm going to go another space over and another space down. And that gives me my point B prime. 1, 2, 3, 4, 5, 2. Okay, I can do the same thing from point A to C. From A to C, it's 1 over and 3 down. So if I'm going to double that distance, I'm going to repeat that movement. Another 1 over, 1, 2, 3 down. And there's my point C prime. And that's the point 1, -2. And if I connect these 2 points together, the line segment should be, oops, let me connect that a bit better. The line segment should be double the length of the original. There we go. That's how a dilation works. It makes something bigger or smaller by increasing the distance that each of the points is, or decreasing the distance if you're making it smaller, from the center of dilation. So this works doing it graphically, visually, with counting the boxes and then repeating the distances. That works even when you're centered at the origin. You can always do that. But it makes it a lot easier when you have a dilation that's not centered at the origin, using our slopes to do that. Okay, moving along. Let me get rid of this. Okay, so you might want to pause the video again and try out the questions on your own, at least the first one. But what it says is that we're first graphing the image of this triangle after a dilation with a scale factor of 3/2 centered at the origin. Our life is easy again because we are centered at the origin. So we could just take each of the points and we can multiply the x and the y coordinates by 3/2. So point R, I'm going to start with point R. Point R is the point 2, 0. So that's the point 2, 0. So to get R prime, I'm going to multiply the x and the y coordinate by 3/2. 3/2 times 2 is just 3. And 0 times 3/2 is 0 because 0 times anything is 0. And I'm going to just plot that. 1, 2, 3. Okay. Let's do S. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. So let's multiply 4 by 3/2. And that is 6. And let's multiply 6 by 3/2, and that is 9. So 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 9. And then finally, point T. That, oh, it's Q. My bad. It's QRS. Why did I think that was a T? That is -2, 2. So if we multiply -2 by 3/2, that would be -3. And if we multiply 2 by 3/2, that is 3. Okay, let me connect that together. And notice how it is about 1.5 times bigger than the original, because 3/2 is 1.5. So the next part is to use slopes to explain why Q prime R prime is parallel to QR. So let me find the slope of QR. So slope is y2 minus y1 over x2 minus x1, change in y over change in x. So 2 minus 0 would be 2. This is for QR. -2 minus 2. And feel free to use your calculator, but I'll do it over here. -2 minus 2 is -4. So in simplest form, that's -1/2. So that's for QR. Now let me try Q prime R prime. So 3 minus 0 is 3. And then we have -3 minus 3. And -3 minus 3 is -6. and that also reduces to negative 1/2. So Q prime R prime is parallel to QR because they have the same slope. And that makes sense because a dilation preserves parallelism, so the pre-image and the image should be parallel to each other. They should have the same slope. A 3-inch line segment is dilated by a scale factor of 6 centered at its midpoint. So here's its midpoint. And the midpoint does split into equal parts. So that would be 1.5 and 1.5. And since we're dilating by a scale factor of 6, from the center of dilation this way, it's going to get 6 times bigger. And from the center of dilation this way, it's going to get 6 times bigger. So there's now 1.5 piece after the midpoint to the left. There's going to be a second one, and a third one, and a fourth, and a fifth, and a sixth. And these are all 1.5 long segments. So 1.5 times 6, that is 9. The same thing's happening from the midpoint in this direction. There's one piece right now, but when we're making it 6 times bigger, that's going to go to 6 pieces because 1 times 6 is 6. That's 3, 4, 5, 6. So once again, there are 6 1.5 pieces, so that's 9. So in total, the whole line segment is going to be 18 when you dilate it by a scale factor of 6 centered at its midpoint. Hopefully that visual helped to make it a little bit clearer. Okay, so we're going to take a look at the next one. Oops, let me make it a little bit bigger. Feel free to pause the video so you can take a look at the questions. So we have a parallelogram, and we're going to do the following transformation. When you see that symbol, that's for composition of transformations. So that means do this one first and this one second, kind of the opposite of the way that you would normally go in. Instead of from left to right, we're going from right to left. So I just plotted the coordinates. The dilation centered at the origin because it doesn't specify, so we assume it's at the origin. So you can just take each of the original coordinates and you can multiply them by 1/2 to graph the new points. So for example, S prime would be half of 2, which is 1, half of -2, which is -1. So that would be the point 1, -1. Take a second and plot the other dilated points by a scale factor of 1/2. I'm going to do that on my end as well. Please pause the video. And then it says to do a translation 4 units to the right and 2 units down. So I'm just going to take each of these points and move them 4 units to the right and 2 units down. Please do that on your end as well. And here I have the final graph parallelogram and the image. Okay, over here we're told that EB is parallel to DC, and we're given some side measurements. And we're told that ADC is the image of triangle AEB under a dilation with center A. And that makes sense because if A is the center of dilation, it's the point that wouldn't change. And that's the point that's in common between the small triangle and the big triangle. And the scale factor, find BC. So I'm going to put an X on BC and explain why EB and DC must be parallel. Okay. Well, the scale factor would be side from big triangle over a corresponding side from small triangle. So this is 14 over 9. So 14 over 9. I don't think that works out nicely in my calculator. 14 over 9. Yeah, that does not work out nicely. I'm just leaving it as 14 over 9. I'm going to use a proportion to find the missing side x. So let me do the side from small triangle over the corresponding side from big triangle. Side from small triangle over corresponding side from big triangle. That would be 9.2 plus x. So I am going to multiply. Let me do this on my calculator. 9 times 9.2. That is 82.8 plus 9x. And then the other way, we have 14 oops, 14 times 9.2, and I got 128.8. Let me subtract 82.8, and that's 46. So I have 9x is equal to 46. So I have x is equal to 46 over 9. That does not work out evenly. That's about 5.1. So I'm just going to leave it as 46 over 9. So x is approximately 46 over 9. And that's okay. And then it says explain why EB and DC must be parallel. Well, it gave us that they're parallel, but also we have similar triangles here, so they have to be parallel to each other as well. But it told us in the question that they had to be parallel to each other. And also they have to be parallel because under a dilation, dilations preserve parallelism. So the pre-image and the image, the corresponding sides will be parallel. So EB and DC, those DC is the image of EB after the dilation, so they should be parallel to each other. You can take a second, pause the video, and take a look at the next question, and then I'll give you the answer. So please pause the video. And the correct answer is answer choice 4. If you take the distance from the center of dilation to the image and divide it by the distance from the center of dilation to the pre-image, you should get the scale factor. That would be the same thing as if you took the length over here and divided it by the length here, you would get the scale factor. That wasn't an answer choice. I didn't have BA over DC. That wasn't an answer choice. So this is the next best answer choice. The distance from the center to the image over the distance from the center to the pre-image. Just to summarize a bit, this transformation would not be a dilation because from here to here, you're multiplying by 2, but from here to here, you wouldn't be multiplying by 2 because 4 times 2 is 8. So if you're not multiplying the coordinates by the same scale factor, it's not a dilation centered at the origin. Under a dilation, the pre-image and the image are sometimes congruent. Usually they're not congruent because a dilation makes a figure bigger or smaller depending on the scale factor. Dilations are the only non-rigid motions. Reflections, rotations, and translations are rigid motions, which means they make congruent figures. Dilations don't preserve side lengths. They change the side lengths, so they don't make congruent figures unless the scale factor is 1 or -1. Then it will make a congruent figure because 1 will keep it exactly the same as the original. -1 will just change the way that it's facing, but it will keep it the same size and shape. The next part of the video is going to be construction, so if you don't want to see dilation constructions, you should end the video now. Here we're going to dilate the triangle by a scale factor of 3. So we're going to take each of the pre-image points and we're going to triple the distance that they currently are from the center of dilation. And that's going to make it 3 times bigger than it is right now. So let me get some more space here so I can have as much space as possible. Okay, so what I'm going to do first is I'm just going to use my straight edge to start at the center of dilation, go through the pre-image points, and just extend a bit after that. Now, the reason I'm doing this is to help me find my image points at the end, because the pre-image points, center of dilation, and the image point should all be collinear. They should all lie along the same line. That's a property of dilations. So by making these straight lines now, it'll help me find the image point at the end. Let me get my compass out. And what I'm going to do now is I'm going to take my compass, and I'm going to start with point X, and I'm just going to measure the distance that point X is from the center of dilation. So let me put my compass, let me put it actually on the center of dilation. So I'm putting my compass on the center of dilation, and I'm just going to open up as best as I can to match up with point X. And then when I find the best match, I'm going to just put an arc to show that I measured the distance. So that's the distance from X to the center of dilation. If I go over here and I repeat that distance, that's going to be doubling the distance, but I want a scale factor of 3, not a scale factor of 2. So I'm just going to go ahead and triple that distance. And right over there is where my point x prime will be. Okay, so I'm going to do the same exact process for points z and y. So once again, I'm going to go over to point A, and I'm going to match up as best as I can to point Z. And I'm going to put an arc to show that I measured the distance. Okay, that's doubling the distance. Let me get some more space down here. And tripling the distance. That is my point Z prime. One more to go, just the point Y prime to go. So let me zoom out my page so I can see everything at one time. Much, much, much better. There we go. That's the distance. Doubling it. And tripling it. So that point right over here is our point Y prime. I'm just going to use a different color line. And what I'm just going to do is I'm going to connect the image points together so that you can see them. And notice how our new triangle is about 3 times larger than the original. The next one I'm going to do is by 1/2. So, and this is the last one that we're going to do together on this video. So 1/2, we're actually going to decrease the distance that each of the points is from the center. That's making it smaller. And it's making it smaller by exactly half. So let me get my line. And what I'm going to do is I'm going to connect, just like in the last example, the pre-image point to the center of dilation. And this time I want to find the halfway point between this distance because the scale factor is 1/2. So I want exactly the middle. So the way I'm going to get exactly the middle is I'm going to do a perpendicular bisector. So let me grab my compass. I'm going to go over to one of the endpoints of this line segment. I'm going to go about 3/4 of the way down. The exact distance doesn't matter. Arc above and below. Without changing the distance, go over to the other endpoint. And same arc above and below. And right through those intersection points is my perpendicular bisector. And that would be the midpoint of that line segment. So that would be half the distance between where x is now and the center of dilation. So that would be the point x prime. This can get a bit messy, so I'm going to be using some different colors for the other ones, especially with point z. I'll just do point z next to get it out of the way. So I'm just going to connect point z here. And now I'm going to do the perpendicular bisector of that distance. Oops. So that's of the green line. So going to put my compass onto one of the endpoints, about halfway down, 3/4, doesn't exactly matter. Then I'm going to move my compass over to the other endpoint, and I'm going to make the same arc using the same distance. And right through here is my perpendicular bisector. So that should be the point Z prime, that middle point. As you can see, this is getting real messy. I'll do purple for the last one. Different colors definitely do help with these constructions. Connecting from point Y to the center of dilation. Same exact process. And here we have our point y prime. I'm going to connect this all together with a totally different color. I'm going to use yellow, that will stand out. So I'm just going to connect my image points together. And notice that our dilated triangle is half the size of the original. That one can get messy. Generally on the Regents exam, it's making it bigger, not smaller.